takes an array of doubles, which is represented by this pointer, ARR, and it's going to be of size n, and all it's going to do is add up all the elements of the array. So it's as simple as it gets, but it illustrates the key points. So what is the strategy to parallelize this? Well, it's pretty obvious. Each core, which is going to be represented by a thread in the PThreads model, is going to sum up some subset of the index space. Okay, so if I have 2 cores and 100 elements, the first core might do element 0 to 49, and the second core might do element 50 to 99. A static decomposition of the index space is adequate in this case, since each core is doing the exact same operation for each iteration, and we expect the processors to perform roughly the same performance level. There could be noise and there can be some throttling, but that's reasonable. To create a thread pool also, while it potentially evens out any fluctuations, also comes with a lot of overhead. So for these type of applications, we usually do a static decomposition. Okay, so it's very, very simple. So what do the steps look like? Well, I'm just gonna initialize the array to whatever. And then I'm going to have to get a bunch of variables into the thread worker routine so that each thread knows what it has to do. Okay, so you do it many different ways, obviously. What I'm going to do here is I'm going to create a structure, and the structure is defined at the top here. I call the structure param, so I just pack all the parameters together. Since the worker routine only takes a pointer to void, I have to sort of pack everything together. And so here, I give each thread an integer ID when I create it. I store ng, which is the global number of points that I'm summing, what I called n below in the main program. And l is the local number that are being summed just by this given thread. And its starting index, so it has to know where in the array to start summing. It has a pointer to the shared array. All threads will have that same pointer. And then it's going to come up with some LSUM, which I call the local sum. Okay, so each thread sums up part of the index space, and it's going to have to return it, and someone's going to have to finish up the job of summing all the partial sums, which is a serial component of an otherwise parallel code. Okay. Okay, so I make some simplifying assumptions when I initialize the values for each thread. So I have NT threads, and each thread is going to have its own unique copy of some of the things in the parameter structure. So the array is just going to be the array. It's the same for each thread. The thread ID, I'm going to go from 0 to NT minus 1. So it's a simple way to say, if you are this thread, do this. Otherwise, if you are that thread, do that. So it allows thread-specific functionality to exist in the worker function. N global is just n. It's the same for everybody, but n local is n over nt. So it's the fraction of the index space that each thread gets, assuming it divides equally. Okay, which is perfectly fine for a simple little example. It's not hard to do the bookkeeping to deal with the remainder. Then you have to say where this particular thread starts in the index space. Okay, so that's just the number of elements that it has to calculate times its position in this array of threads. Local sum, initialize it to 0, and then call pthread create. And when you call it pthread create, you have to pass it a pointer to the handle. We're going to use null for the parameter configuration, to give it a function pointer to where the work is going to be done. And you're going to have to give it an input argument. And I'm going to cast a void, a pointer to the parameter array that I just configured. And that, by the pthreads library, gets passed then into this void argument here, which I turn around and cast back to a params argument. So now when the thread is executing this work, it has access to all of those values. Some are specific to it and some are shared. And that was just implicit in what I shoved into that params array. Okay. And so all the worker function is going to do is it's going to say, okay, give me my starting index, my particular value p.start for the particular thread that's executing it. My end is just start plus the number of points minus 1. Now loop over my index space, and the local sum, which started at 0, is going to be the sum of all the array elements in that index space. Okay. So that's really it. Then with thread, the work of each individual thread. So when each thread finishes the work function, and it has the option of returning a void pointer, it just returns null in this case. That's the way I've done it. There are obviously, you could use the return type for the local value, many different ways to do it. But the local value is put into the structure. So upon return, it exists. And then I call pthread join, which is going to wait until the ith thread, so starting with thread 0, will wait for thread 0 to finish. And then the main thread is going to add the local sum from thread 0 into the global sum. And then we'll wait for thread 1 to finish and so forth. And since they all finish about the same time, there's not much opportunity to optimize this. You could just say, whoever finishes next, accumulate and not wait for thread 1 to finish and then thread 2, but that's not going to make much of a difference in practice. And you amortize a lot of these costs by making the array very large. Otherwise, you're not that interested in doing this anyhow. And you're not usually summing the elements of the array. You're usually doing something that is more floating point intensive. So these costs become cheap relative to the core costs of iterating over the array and carrying out the numerical operation. Okay, so this is going to be an inherently serial operation here, but it's still mostly parallelized. And we print the global sum, and then we call pthread exit, which is, for this particular application, it's not necessary here. You could just end main also. Okay. So that's one simple way to do it. Let me just show how to compile this. So gcc minus pthread rsum.c minus rsum. And then I said how many, how big the array is. So it has to be divisible by the number of threads. I think I said, kind of forgot how many threads I said. 4. Okay, so I'll do something like, boom, okay. And you could check that that's right, but I think the answer is correct. And if you run it with 1 thread, that's always, I can't specify the number of threads. If I had allowed the number of threads to be something you could specify, you always want to compare the serial answer to any parallel answer. And that's how we'll test. That'll be one of the first tests we run on your homework problems. Anyhow, so that's the idea. And you can look at the code, and I think it's pretty simple once you understand how the data moves in and out of the thread function. And the synchronized write is done in serial, so there's no real problem. But now I'll show you in the next version a way to do the synchronized write, which is, potentially more efficient, though in practice it won't make a huge difference. But that requires a little bit more infrastructure. So let's switch to that example. And this will be version 2, and it's doing the exact same thing. Okay, I have a structure called params. This time, though, I'm going to create the variable gsum outside of any function. And when you do this in C, it becomes a global variable to all the functions that come after it in the program unit. So I know you're told as a software engineering kind of truism to avoid global functions. Of course, that's not, one, that's not true, and two, it's not really global in the sense it's just global to the compilation unit. So you can think of it maybe analogous to a public variable in a class. So that's perfectly fine. And I'm going to create this pthread mutex t type that I told you about in the notes. That's going to allow me to lock an operation. Okay, so that's going to be the main difference here. Otherwise, I do all the same regular steps. I call this mutex init function, and I pass it a pointer to the mutex sum, which is an instance of that type, and I just pass the parameter null for default configuration. Okay, what that's going to let me do when I'm in pthread create is, if I look at my worker function, I do the exact same thing I did. I loop over my index space, but now I'm going to use that lock, which is globally available to all functions, to do a synchronized write. So what does that mean? That means I'm going to ask for the mutex here, and I'm going to accumulate into gsum the local sum of whatever thread this is. And if there are 3 different threads working on the same thing, and one of them happens to be trying to do this at the same time, it's going to attempt to obtain the lock, and it's going to be locked out. So it's going to have to wait until this particular thread releases the lock, and then it can enter and it can add in. So this creates a safe operation. The problem being that you have, in this case, 4 different threads, each of whom has its own local variable LSUM, and they're all accumulating it into one global position in memory GSUM. And that operation can be corrupted if it's not done as in a transactional way, if it's not done as an atomic process. Okay, so this is the technique that you use to do that, and then you don't have to do the serial operation at the end of the code. You just have each thread contribute as it computes its sum. Right, so when you come back up here, you just call thread join, you print the global sum, and you're done. So I'll look for the same compilation here. I'll run the same test. No, it doesn't look like the same answer. So let me see if I had the same. Let me just look at this for a second. If I initialize it in the same way, I'm not sure I did. I was just playing around. Let's see. Yeah, I didn't initialize it the same way. So let me go grab the initialization from the other one for peace of mind. So we'll grab that from there, drop it in here. Compile. Okay, and I think that's the same answer that the other one got. Yeah. Okay, so it looks good. All right, so that's just a really simple example. It's enough to be able to do the end body example, which is a much more fun problem, and actually a problem that is very relevant for many different fields of computational physics. So you won't find it too hard to do, but it takes a little bit of finesse, and you have to be careful about some things. And then what gets really interesting is measuring the performance. So I'm hoping people will put some thought and some care into how they do that, and I'll give some guidance on that aspect of it as well.